Good evening, everyone, and thank you for coming to our gallery. Today we have a very special program that has been in the news and in minds of a lot of us in the arts field and beyond. Certainly Hollywood has taken notice of AI. So, Barn Gallery, Ogunquit Arts Collaborative, is our mission to bring in things that are current, things that are affecting artists in our gallery. So welcome here tonight. Anthony Alvey, one of the Ogunquit Art Association artists. I'm Deirdre Flaherty, president of the OAC and an OAA artist too. Anthony's going to introduce to Stephen. So Anthony.
Hello, everyone.
Hello.
Thank you for coming tonight. This is for me a really exciting topic, as I'm sure it is for you, which is probably why you're here. Like Deirdre said, this is something that's on the forefront of our minds. And I mentioned it to some of the students in my class, and they were asking me about Skynet and robots taking over. So we'll see what's going to be happening. But nevertheless, this is Chase Stevens, and he has a master's degree in artificial intelligence technologies and has worked with several startup companies in the field of technology, in the field of artificial intelligence, AI. He is a working expert in the field, and so I'm real excited and happy to welcome Chase. So, the floor is yours, sir.
Thank you very much for the introduction. All right, well, just to reiterate, thank you all so much for attending. I won't give too much of a preamble, but just to, again, express my gratitude to the Barn Gallery for hosting this and to Anthony for helping sort of get this set up and organized. So quick round of applause, if you don't mind, for those. So tonight I'm going to be talking about AI-generated art. And specifically, I'm going to be focusing on image generation. But I do want to emphasize, and I'll be touching on this briefly at various points. As you've probably seen in the news, the advances into AI aren't just touching image generation, but a wide swath of different fields. Basically, anything that can be digitized, AI is now being applied to. So that includes music generation, writing, predicting the weather, whatever you can think of, right? So what I'm going to be talking about is geared toward the image generation side, but this is sort of got its tendrils in everything these days. And a lot of the same principles apply widely to all those other fields. So with that in mind, let's get started. So first, what is AI-generated art? What does that mean, right? I've got an example here. So this is generally what people are talking about when they're talking about AI-generated art. You provide some prompt, some text of what you want the computer to make for you. So it's a little hard to read, but here I've written Rococo-style interplanetary rocket, just as an example. And you can see this particular AI, what you might call a model or a generative model or a neural network, has produced 4 different sort of sample images. It's just a free online tool that anyone can make use of, right? And you can see it's generated what looks like a painting of a rocket in the Rococo style. This is maybe some upholstery on furniture, and these are, what would be presumably era-appropriate rockets, right? As another example, this sort of gives you an idea of the wide array of what you can make with these sort of tools. So in this case, I put in line drawing of, with heavy cross-hatching of an elephant wearing a top hat, right? And you can see, not only is it able to generate what I'm asking for, but in the style that I'm asking for. And just as a little example, this is Perkins Cove Ogunquit being attacked by a giant squid. So anything that you can imagine, pretty much these sort of tools will do their best to generate an appropriate image for. And the advances in this have been sort of gradual over the last 10, 15 years, and then rapid over the last 2, or especially last year, since 2022. So just to give you an idea of what the pace of this has been like. This is the prompt here, street style photo of a woman shot on Kodak. So this is from July 2022, and you might not be able to see the details in these lighting conditions, but If you were to look at this more closely, the person's face is not really correct. There's some very strange features to it. It's from my perspective, having followed this for many, many years, extremely impressive. But if you see what this same prompt will produce now, this is, I would say, a nearly photorealistic or maybe just flat out photorealistic rendering of a woman on the street, right? And to emphasize, this woman doesn't exist, the street doesn't exist, no human was involved in creating this image. This is just purely, you gave it this text and it produced something that I think most people would be hard pressed to distinguish from an actual photograph. Just to give you some more examples. So this is from June of last year. Greek philosopher coding on ancient computer. I mean, this is sort of cartoonish and fun, but that same prompt today gives you something that's, like I said, nearly photorealistic, amazing. And again, apologies for the lighting conditions. And even over the last year, there have been sort of very gradual advances. So this is a woman sitting in a coffee shop, and you can see that, or maybe you can see, over the last few months, there have been iterative improvements to these types of what are known as diffusion models that have made it get better and better and better and better. Just one more example here. This is a woman by Wes Anderson, right? And again, last year, January, looks, maybe like a painting in a Wes Anderson-esque style. This bottom image here from this month, I just saw Asteroid City a couple weeks ago, and I'd be hard pressed to distinguish that from a still from that movie. If we go back even further, this really highlights how rapid these advances have been. So first of all, let's say 6 years ago, which is where the left-hand side's from, we didn't have models, we didn't have AIs that you could give a whole sentence to. Instead, you would train them on a category of objects like flowers or dogs or something like that. They would produce results for that category. It had to be specific to that category, and they were not that great. So to zoom in on some of these, you can see these are blurry, they're not very high resolution, they are kind of flower-esque, but I mean, compared to today, it's night and day, right? And I could go back even further, but it wouldn't, past 6 years ago, the results are useless. You might also have seen AI in the news and generative models of this sort in the news. So this was back in May. I don't know if anyone caught this, but essentially what happened was that there was an AI-generated photo of an attack on the Pentagon that went viral online. And that morning, because of this, the S&P 500 took a little nosedive. It recovered after people realized that this wasn't a real image and there wasn't an attack on the Pentagon. And in all candor, this is not necessarily something that is specific to AI. So you could make the same sort of thing in Photoshop or something like that and produce the same effect. But certainly in the future, there's going to be more and more AI-generated photographs of events that never happened, never will happen. They're going to make impacts on the world and society.
Hey, Chase, sorry to interrupt, but I was just thinking about the lighting situation. Maybe after the fact, I can post a link to the PowerPoint.
Yeah, absolutely. And I should have this recorded as well, so if folks want to take a look after the talk.
Okay.
There have also been a lot of headlines in the news about some of the legal and ethical ramifications of AI, right? So a lot of headlines about, does this violate copyright? Question about, is this going to take jobs away from artists? Even art, is it original, or is it just sort of copying and pasting things from that's seen elsewhere? I think as we were discussing very briefly at the top of the talk, right now there's strikes by the Writers Guild of America and the Screen Actors Guild of America and I don't think it's their main focus, but one of the things they've been talking about is, hey, we need some assurances that we as actors are not going to be replaced by AI models, or we as writers are not going to be replaced, or voice actors, or what have you. So in this talk, I'm not going to try and sway you one way or the other on these topics. I'm hoping to give you enough information to be able to form your own opinions about these. Or at very least, next time you're at a dinner party and this comes up, to be able to have an informed conversation about how these models actually work and how it is that they produce images. So with that in mind, I'm just going to give you a brief overview of what I'm going to talk about tonight. So I'm going to start off just giving you a very top-down, broad overview of how this process works, right? How we go from text to image. Then we're going to talk a little bit about, well, how does a computer represent images in the first place? Not, AI models specifically, but just any computer. We're going to be talking about neural networks, which is sort of the machine learning technique that has powered the rapid innovation in AI over the last 10 or so years. How we can encode the words that you provide, the prompt you provide for the neural network, how the neural network manages to denoise images, and that'll make more sense in context once we get to that component. And then finally, just capping off, some possible implications for society and the arts later on. So, the other thing I will mention before we get too deep into this is that under the hood, AI is math. So there's going to be some math in this talk. Before you start reaching your pockets to try and find your keys, I solemnly, I pinky swear, I won't be using anything more advanced than basic arithmetic. So addition, subtraction, multiplication, and division. So if you can follow along with that, you should be able to follow along with the math in this talk. So what does this process look like? So we start off with two things. We start off with the prompt that the user is given. In this case, I've chosen Christian Bale fighting a kangaroo, and an initial image. So you have to begin with, at least in these state-of-the-art diffusion models, some sort of initial image. That initial image is random. It's static, like you'd see on a television. You take the text first and encode it. You then take this image and run it through two quote-unquote denoisers. The idea behind the denoisers is to try and reduce some of the static in the image, which you might be a little bit confused about how that works when it starts out being entirely static. We'll talk about that a little bit later. To one, but not both of these, you give the encoded text. They both produce some output, which is sort of the image that's trying to create. But because one has been given your prompt and the other hasn't, there'll be some slight differences in those. We compare those differences. We amplify the parts that are only found in the output of the denoiser given your prompt. And then we somewhat cruelly add noise back into the model, right? So we take this nice image the model's trying to produce for us, and we make it more static. And we put it through the same process over and over and over again, making it a little less noisy, a little less staticky every time. And so you do this for multiple iterations, and at the end, it's about the image that you wanted. So just to recap what we're going to be discussing. First, we have to talk about, just to lay some groundwork, how do computers represent images at all? Second, what is a neural network? Because the encoder and the denoisers are built using neural networks. Then, how do we take your initial prompt, Christian Bale fighting a kangaroo, and code that as numbers for the computer? Then, how do we denoise the image given your prompt? So, how does a computer represent images? This is an image from a computer's perspective. Any guesses on what it represents? So this is a photo of Albert Einstein, very low resolution photo of Albert Einstein. I'm going to overlay what I just showed you here, if you were to really take your time and inspect this, you would notice some patterns in how the pixels of this image, the discrete bits of it, correspond to the numbers. So for black and white images like this, the way they're represented is darker parts of the image, darker pixels, have a lower number associated with them. And brighter ones have a higher number. So fairly straightforward and simple. And if we take a look, this is what is known as a quote-unquote grayscale palette. On most computers, the numbers range from 0 to 255. That's just sort of an artifact of how the computer architecture works. In the past, you would have had very few, even in the grayscale case, colors to choose from, maybe 8 or 16 or something like that, but now it's generally 0 to 255. Generally speaking, nowadays we're interested in more than just black and white photos. We also want to have color photos. So the way this is handled by the computer, if you will think back maybe to some of your art classes, or I'm sure some of you will be familiar, when you're dealing with light, using just red, green, and blue, you can create essentially any color that you like within a certain range, right? So if either in the total absence of any of those sort of, in this, I'll say primary colors, you get black. If you are emitting all of those, then you get white. And what's happening on your computer screen when you're looking at is, and this is easier, unfortunately, to see in the older, CRT monitors and stuff like that. But you really try, you can see them probably not on a phone screen, but on a desktop screen. There are basically thousands and thousands and thousands of little clusters of light bulbs, red, green, and blue, and they light up different amounts depending on the image you're trying to display. So in order to represent a color image like this fruit stand here, what we do is we first split into red, green, and blue components, which is, if you think about it, sort of the same as putting a gel, a red, green, or blue gel in front of the image. And then we look at the brightness, and we simply encode that as if it were a black and white image. And then when you go and display this, you reconstruct and choose the voltages for the various LEDs, dependent on these red, green, and blue channels, as they're called. So just to direct your attention a little bit and help us be a little bit more intuitive, if you look at the apples here, red apples, you can see in the red component, they're very bright. In the green and blue, they're very dark, just to illustrate. All right, so now we know how images are encoded. Just generically, this applies to any computer pretty much. Now we have to talk about neural networks. So to begin with, there's a distinction between natural biological neural networks and so-called artificial neural networks. When people say neural network, they mostly mean the artificial, but it's inspired by the brain. This is a single neuron, a brain cell. How a brain cell works is it has these dendrites. These are sort of these tendrils that are feeding into the main body of the cell. There's this axon, which is sort of coming out of the cell, and it has terminals which connect to other brain cells. And what happens when one of your neurons fires in your brain is there's literally an electrical voltage that goes through this neuron. So there'll be other neurons attaching to these dendrites with their axons. And one of two things can happen when those other neurons fire and provide some electricity to this brain cell. One possibility is that it's not enough voltage. So in the case of a neuron, there's some level of sensitivity. That level of sensitivity varies for every neuron in your brain. And if the input voltage is less than that level of sensitivity, nothing happens. But in the other case, the neuron is almost like a gun. So there's a lot of power that's been stored up, ready to deploy, and depending on how much activation, how much weight you put onto the trigger, it's either going to fire or not. In the case where it fires, a huge spike of voltage is emitted and travels through this axon, down through the axon terminals, into the other brain cells it's attached to. And then, there's a little bit of a refractory period, and then it's ready to fire again at some point. So that's how a human brain cell works at a very simplified level. In the 1940s, late 1940s, researchers wanted to try modeling this brain cell in an artificial way. So as opposed to a neuron, they came up with a perceptron. And a perceptron is an even more simplified version of this neuron. But the basic idea is, like the neuron, you have inputs, you have weights attached to those inputs. So basically how much or how little it's going to affect the firing of that cell. You have a threshold value for the perceptron. So this is akin to the sensitivity of the neuron. And then you have an output. And because this is, needs to be implemented on I'm lying a little bit. The first implementations of this were just in pure hardware, just wires. But nowadays we implement them in software on a computer. And so we can't just sort of hand wave away what this is doing. We need to get into the nitty gritty of how this is implemented. So it's actually very simple. Like I said, it's lower school, middle school, elementary math. So the rule is, for determining what the output of this perceptron is going to be, is to look at each of the inputs in turn. So let's say the very first one I've labeled I1, and multiply it by the associated weight for that input. So I1 times W1 plus the next one, I2 times W2, the next one, I3 times W3, so on and so forth. And depending on how you set this up, it can have as many or as few inputs as you like. But each input has an associated weight that's going to dictate the influence of that input on whether this perceptron fires or not. Just like the neuron, there's some sort of sensitivity. This is a threshold value I'm calling T here. You add that on to all of this. And the very last step is, before you output it, just like the neuron, you have to decide, is this going to fire or not, based on the inputs and the weights and the threshold. So you just do a quick check and see, is the value you get from adding all those together, all those products together, greater than 0? If it's greater than 0, we consider it to be fired, to have fired, and we produce a value that's the result of this equation, right? If it's below 0, then we just cap it off at 0 and say nothing happened, it didn't fire. So this is going to be, I'm sure, very, or this is a little abstract, just in vacuum like this. So let me help illustrate a use of this in the real world. So for a single perceptron, one thing we can use this for, and I've set this up specifically with 3 inputs, is processing images. So here's an example. We can treat this as the red channel, the blue channel, and the green channel of an image. And let's say we have one pixel here that's sort of this periwinkle color. We can try and convert that to black and white, to a grayscale value. You might be surprised to learn, it's just a feature of human cognition in the brain that when you're looking at something, the different wavelengths of light affect your perception of how bright it is differently. It's not sort of an equal amount type of thing. So for instance, green light you perceive as being more brilliant, more bright than red light or blue light. So for the sake of this example, when calculating the quote-unquote luminosity, basically what you want to do when you're converting something color to black and white, you weight the green channel by 70%, you weight the red channel by 20%, and you weight the blue channel by 10%. So we're going to take this periwinkle pixel, we're going to, and one last thing, the threshold for this case will be 0. Take this periwinkle pixel, we split it out into the corresponding red, blue, and green channels. We feed those values in, so you can see them here. And then we can just go through the calculation that I've outlined, multiply a bunch of numbers together and add them all up. And the end result, it's a little bit cut off here, but it's 134. That doesn't really mean anything, but if you interpret that as a value between 0 and 255 for your black and white image, this is the pixel you get out. To, sort of what you'd expect, a gray version of this periwinkle pixel. So you can imagine going through an image, here I've got the Mona Lisa, and just going pixel by pixel, applying this perceptron to each pixel to get a black and white version of that image. And if you were to do so, based on the equation I just gave, this is what you get. I haven't really covered the influence of this threshold value, the sensitivity of the perceptron yet. To help illustrate that, let's just, for the sake of argument, make this -99. So what that's going to mean is you have to have a lot of oomph, a lot of power from the inputs to be able to trigger this perceptron. If we do that with that threshold and apply it again to the Mona Lisa, it's not so easy to see, but we get something where basically all the darker colors have all been squashed together, and so you've lost a lot of the details in the darker regions of the image. Just to compare, oh, I'm sorry, you can't really see it unfortunately, but later on when you look at these slides in your leisure time, you'll be able to see half of this is the original image and half of this is the image with the threshold value set.
Can I ask?
Yes, please.
So you've gone from color to black and white.
For the sake of this one example, yes,
Okay.
yes.
You've taken out the pigment.
Yeah.
Make it black and white.
And yes, and
Formula.
if we were to do this in a very naive sort of way, and just say we're going to split out those red, green, and blue channels, and we're going to just average the values, let's say, you wouldn't get something that looks correct to the human eye. You wouldn't get something that looks like a black and white version of the image. You get something that was sort of strange and distorted and not quite right. Does that help explain? Yeah. Okay. Just a sidebar here for anyone who is familiar with Boolean logic or propositional logic, maybe has taken some philosophy courses, or alternatively is a little familiar with electronics and has worked with circuitry before. I've got 3 perceptrons here, 2 with 2 inputs and 1 with 1 input. Transpires, and this is just sort of an academic note, these correspond directly to an AND gate, an OR gate, and a NOT gate. That doesn't ring a bell, don't worry about it. But the point of this being that these 3 components in electronics or in logic can be used to create any arbitrary circuit and do any sort of arbitrary computation. So all this just to say that these perceptrons, if arranged in the right way, can do anything any other computer can do. Just as a note. So these are very, very flexible systems if you set them up correctly. So going back to the human brain, one of the most important features of the human brain is that you have more than 1 neuron, or most people seem to have more than 1 neuron. So you don't only have this 1 neuron in your head, you have this neuron talks to other neurons, which talk to other neurons, and so on and so forth, right? And a single neuron firing can cascade out and activate whole regions of the brain. I think in the human brain, it's something on the order of 700 billion-ish neurons that you have. Those are just the neurons, not including the connections, multiple connections between them. And that's sort of what makes the brain useful. Likewise, for neural networks, we don't typically work with 1 perceptron, or at least since the 1990s, we don't work with 1 perceptron, but we put bunches of them together and wire them all up in different ways. And there's a lot of variation in this potentially. You can set them up in a lot of different ways, but the most typical structure is to put them in quote-unquote layers, right? So perceptrons that will all be calculated at once, that feed into a next layer, that all are calculated at once, so on and so forth, right? What is that good for? What do we use these type of neural networks for? Again, another example. So here I've got a sort of low resolution image of a handwritten number 7, right? And I'm actually going to take an example from real life. Back in the 90s, there was a researcher who was trying to employ this technique to be able to read postal codes, handwritten postal codes off of envelopes. So his ambition was to take this technology and be able to read automatically the front of that envelope and get the zip code from it to help sort the mail. So the ambition is to take this handwritten digit, which has already been pixelized, and convert it to the actual digit, 1 or 2 or 3 or so on. Try and figure out which one this handwriting represents. So a way you might be inclined to do that is to just take every one of these pixels. This is a 28 by 28 image, so that's 768 in total, and pretend it's an input to your neural network. Then you feed those into multiple other layers. So I didn't draw all the connections here, but just imagine all of these are connected down the line, so on and so forth. And the very last layer, you look at the outputs of that, and you interpret them as how much the neural network thinks this is a digit 1 or a digit 2 or digit 3, so on and so forth. So for instance, in this case, the neural network might say, all right, well, this, it looks a little bit like a 3 maybe, it could be a 4, could be a 9, but mostly it looks like a 7. And so you would go through and interpret this and say, all right, I've put this image through, I've done all the calculations at the end, the 7 neuron is what's most active, so I'll interpret that as being 7. So crucially here, as opposed to the last example where we were talking about making a color image black and white, I haven't told you what any of the thresholds for any of these perceptrons would be, or what any of the weights are. And you can imagine if you were trying to determine those manually by hand, it'd be quite a challenge. So what we wanted to do is to have the computer determine those on its own, and somehow be able to figure it out based on examples we give it. So the way this works is you have to start off with what's called a quote-unquote training set. So these will be what we call labeled examples. So multiple different handwritten images of digits in this case, and then paired with what digit the person was trying to write. And the procedure for having this computer learn the patterns there and suss out how the pixels relate to the digits is surprisingly simple, scarily simple. So I'm going to talk about one method. This method does work. It's not the most efficient method, but just to, this will be fine for the sake of this talk, and will work in practice, just not very efficiently. So a way you can do this is you take all of your labeled images, so all your pairs of here's the image of the digit and here's what's supposed to be, and you run them through a neural network that starts off with completely random weights and thresholds. You just pick them out of a bag, between some range, like -1 and 1 or something like that. You don't have any expectation it'll work very well, and you have some means at the end of grading it. So in this case, it might be, well, how often, what percent of the time to get the digit right. And at the very beginning, you'll be terrible at this. I'll give it a D+ here, just for the sake of illustration. So that's your starting point. The next thing you do is you copy that very first neural network, and you, again, get out your dice and make some random changes to your initial neural network. And there's a multitude of ways you can do this, but you can imagine, well, maybe just one of those weights or one of those thresholds I'm going to change quite a bit, or maybe I'm going to make little tiny changes to all of them. It doesn't really matter. Well, sorry, it can matter quite a bit, but all of them will work in some capacity. Any of those strategies work in some capacity. The point is you just make a very slight perturbation to what you had as quote-unquote parameters, the weights and thresholds for this neural network, and do the same thing you did the first time. Run all of your examples through it and see how well it does. And one of two things will happen. So either it will perform better than you started out with, in which case you keep it and you copy it over and start from there, or it did worse, in which case your changes were bad and you throw them away and start over again. But the point being, you just take this initial random thing, see how well it does, make some random changes to it, see how well those do. If it's better, keep it. If it's worse, toss it and do the same thing over again. And you keep doing this over and over and over. And I see some skepticism maybe in the crowd. It sounds too good to be true and too simple, right? If you were to sit down and do this at a desk and were hand writing all these equations and doing this work, it would take a very long time to find a random combination of numbers that happens to do what you want to. The trick is, and this is really what's propelled, I mean, there have been advances in how much data is available, there have been advances in the techniques, but really mainly what has propelled the advances in AI, especially in the last couple of years, is computers get more and more powerful, and a computer can do the same sort of procedure millions of times a second, right? And evaluate all sorts of different combinations of weights and thresholds. And so really you're just sort of dumping computer power at this job, randomly rolling the dice, trying things over and over and over again. And by just sort of taking this brute force approach, you can end up, even though it's very improbable to happen upon some numbers that will work, if you do it enough times, very improbable things will happen and you'll get a solution. So, with that being said, now hopefully you have some insight into how neural networks function. And again, just to reiterate, those are what we are going to use for the text encoder and the image denoisers. So now let's get into how we encode words as numbers. So my focus during my AI master's was in natural language processing. And the thing I found myself when I was explaining what that means to people over and over and over again is, well, computers don't come out of the box speaking English. People try and make it, create the illusion that they do, but they don't understand language. We have to find a means of conveying language to them. So this is how, for instance, if you're sending an email or a text message or reading a news article online, this is how, generally speaking, the words you're reading are encoded. Very basic setup. You have a number that corresponds to every letter, and it's just a string of those numbers, right? So here, this is the quote-unquote ASCII encoding scheme. That's not important, but the first column here is showing you the numbers in decimal. The second is their hexadecimal representation, which is, immaterial for this. And then the last column here is what these represent. So you can see at the very beginning here, there are a lot of, I don't know, sort of junk characters, things that you would never read or things that don't correspond to letters. Then there's a bunch of punctuation, then some numbers, then uppercase letters, and then lowercase letters. So here, instead of 0 to 255, we've taken the range from 0 to 127. But the point being that each of these is mapped to a letter or punctuation or something else, right? Why can't we just use this same thing that we use already for email and the news and basically all the other text you encounter when you're using a computer for neural networks? Well, to illustrate, let me show you two words. So this is zebra encoded using that scheme. So you can see, again, every character has a unique number that corresponds to it, and the word hello, just for illustrative purposes. So recall from when we're talking about neural networks, we're going to be taking these as inputs, and we're going to be doing a bunch of math on them, right? We're going to be adding, subtracting, multiplying. So it'd be really nice if the way we represented the words in the first place was amenable to those sort of mathematical operations. If you treat the words like this, it doesn't work out. So if you take just naively, again, the numbers representing the letters in zebra minus the numbers representing the letters in hello, you get just junk out. Some of these are negative numbers. Some of these are things that, none of these are letters, let me put it that way. So it doesn't really make any sense from that standpoint. And the other problem is, so I didn't mention this explicitly, but when you're training a neural network, you have a fixed number of perceptrons that you start out with, and weights and thresholds for all those perceptrons. This particular way of representing a word isn't very amenable to that architecture. So if we're trying to give this neural network with 3 initial perceptrons in its first layer, the word I, this is fine, right? We take E and give it 101 and Y and 121 and E 101 again, and you can feed those in as inputs, and that'll work out fine. But imagine you have the same sort of 3x3 neural network, and now you're trying to fit in castle. Well, there's only spots for 3 letters here, so what's going to happen to TLE? It's not going to work out. You could maybe imagine, well, I'm just going to add some more perceptrons and imagine there are some weights for them, but those weights are not going to be trained and so on and so forth. Just trust me when I say this is not a good way to represent the words from the computer's perspective. So let me show you an alternative. So generally speaking, when we're trying to encode words for a computer, we're doing that by capturing statistical relationships between words in large bodies of text. So if you were an engineer trying to create one of these systems, you would find as much text as you can. You'd get books, you'd get news articles, you'd get Wikipedia, everything you can throw into it, and you would try and have the computer understand what the words in those articles or text mean by looking at how they co-occur with each other, how they relate to each other. So in this instance, I have this huge body of text, these 6 sentences, and we're going to pretend these are the only 6 sentences in the universe for the purposes of today. There are 8 unique words in these sentences. I'll go through them very briefly. So this is the cat purrs, the dog barks, the boy pet the cat, the boy pet the dog bit the boy, and the cat bit the dog. Beautiful story. So if we want to, for each of these words, have some sort of representation the computer is going to find useful, one way of doing that is the method I'm about to show you. So let's take our 8 unique words and put them on one sort of axis of a table. And we're going to have the other same 8 words as the other axis. And what this is going to end up being is for every word, we're going to have 8 numbers that represent that word. So it's not going to matter how many letters the word has or anything like that. Every word is going to be 8 numbers. How we're going to get those 8 numbers is by, again, looking at the statistical relationships between the words in these sentences. So let's start off with barks. This is going to be the word we're trying to create the representation for. The very first step is find all the sentences where barks occurs. So in this case, there's only one sentence, the dog barks. And then for every other of these 8 words, we're going to see how many times that other word appear in the same sentences. So for barks and barks, 100% of the time when barks appears in a sentence, barks appears in a sentence. It's tautological, right? So for all of these, they're going to be, when comparing them against themselves, they're always going to show up with themselves because they're always in the sentence they're in. To move on, for bit, for instance, well, in 0% of the sentences where barks occurs, does bit occur. So we put 0 there. Likewise for boy, likewise for cat. For dog, it's 100% again. So there's one sentence where bark occurs, and that one sentence dog also appears. So 100% of the time when we see barks, we also see dog. 0% for pet, 0% for purrs, and same as with dog, 100% for the word the. Bit is a little bit more interesting because we have 2 sentences. So for barks, in neither of the sentences where bit occurs does barks occur. For boy, there are 3 sentences with boy in them. In one of the 2 sentences where bit occurs, boy occurs. So we put 50% here. Same case for cat. And in dog, it turns out that in both sentences where you have the word bit, we also see the word dog. And just to emphasize, this is not symmetrical. So for dog, for instance, versus bit, there are 4 sentences with the word dog, 2 have the word bit, so 50% here as opposed to 100% previously. So now we're going to go through each one of these in terms. No, I'm just kidding. This is what, if you go through this whole process, this is what you get out for values, right? So now if we wanted to hand one of these words over to the computer, we would just read off this particular row and we'd say, all right, dog is 25%, 50%, 50%, 25%, 100%, 25%, 0%, 100%. And that's how we're going to represent to the computer. This is what the inputs are going to be. Why have we done it this way? What did this buy us? Well, let me show you a little bit of a magic trick here. So I'm going to show you the result of taking our representation for the word cats, subtracting the representation for the word purrs, and adding the representation for barks. So if you'll recall, this didn't really work out so well in our zebra versus hello example. So hoping for a better result here. So I've just taken, first of all, cat from the previous slide. This is what we got for the 8 numbers. We're going to take the word purrs, again from the previous slide, and subtract the values from purrs from the values for cats, right? We're just going to go through every column and take the top number and subtract the bottom number. And these are what we get out for values. And you see things are getting a little strange here. We're getting negative 77. The computer doesn't care. Don't worry about that. That's fine. Now we're going to do the same thing, but adding barks. And again, if you were to go through in every column, do that. These are the final 8 numbers you get. So this is our representation of cat minus purrs plus barks. Now let's do something interesting. Let's compare this against the original word that we started out with, cat. So what we're going to do is just look at the values for each column and just say how much would you have to add to one to get to the other value, the sort of the distance between those two. I'll spare you going through this, but these are the numbers you get out. Basically, there are 4 columns with 100 and the other 4 are 0. And if you sum those all up, you get 400. So this is our, what we call a quote-unquote distance metric. This is somehow representing how close are we with cat minus purrs plus barks to the original cat, and the answer is 400 units. You shouldn't attempt to interpret what this means. There's no sort of real world correspondence to this sort of Manhattan distance metric. So just take it, you can imagine this as being, you know, it's 400 miles or 400 inches or whatever you like, whatever's going to be most intuitive to you for how distant these two representations are. Now, just to put a cap on things, let's do the same thing we did comparing cat minus purrs plus barks, not to cat, but to dog. If we do that and go through the same procedure and subtract the numbers and try and figure out what the distance is, the end result is that the distance is unfortunately a little cut off here, but is 252 rather than 400. So the way you should interpret that is by taking cat, subtracting purrs, and adding barks, we get something that's closer to dog than it is to cat. And I'll spare you, but if you were to go through all the other words, it turns out that cat minus purrs plus barks is closer to dog than anything else. Why? How that? Oh yeah, Anthony, go ahead.
I was just gonna. This is incredibly technical stuff that might be over some of our heads. Could you summarize in a simplified way, like what this actually means?
Yeah. Well, let me show one.
Maybe I can try. Whenever you're ready. I don't know.
Go ahead.
So is this? We have concepts in our brain, how our human brain cells function, and this is a way of establishing a numerical language for computers to interpret.
You can imagine that might be, so for my taste, that's a little anthropomorphic, but that's a totally reasonable interpretation. You shouldn't go overboard with that because you can get into some trouble, and we'll see later on how just because it looks like something that humans do in their minds, that's not necessarily what's going on with the AI, but that's like a very useful correspondence, yes. And probably when humans are learning language, there's something like this, a lot more sophisticated than this, but something like this going on. Yes?
So you're saying this is not like the neighbor coding.
No.
Code writing, just got no.
No, that's much more akin to what I was showing earlier, where we just have for every letter, there's a certain
Yeah,
code.
yeah.
I'm not intimately familiar with the details of the
Yeah,
lingo
okay, so
schema, but
this is dealing with percentages and weights.
yes,
Of occurrence.
yes, it's trying to sort of create something, a mathematical representation of a word that we can use operations like, in a semantically meaningful way, operations like addition and subtraction on, if that helps.
So addition and subtraction are the only things that has been we've had in our experience prior. This is
As
all-
humans?
This is all.
No, I wouldn't say that for humans, but I'll give you another example if this isn't as illustrative as you might like. The famous paper that established a result very similar to this was called King minus man plus woman equals queen, right? So the idea is that we're going to try and find some representations where we can perform these mathematical operations, and what we're doing makes sense on a human level and to the computer both. Does that help?
Yes.
Good. So just to put a little bit of a cap on this, to help understand on the mathematics side what's going on here and illustrate that, let's just look at two of these columns. So the barks column and the purrs column. I'm going to chart these. I'll go through this pretty briefly, but if you chart all of these words on these two axes, barks versus purrs, with barks being 100% barks and 0% purrs, and vice versa for purrs, subtracting to any word, subtracting purrs and adding barks is equivalent to, on this diagram, moving in this direction along this arrow. So going literally from the dot for purrs here to the dot for barks. This direction of motion, if you start off not at purrs, but at cat, brings you to cat minus purrs plus barks. And you can see that the point we end up there is closer to dog than it is to cat, if that helps pump your intuition at all. And likewise, you can look at different columns, so the cat and dog columns, and do the same thing, same operation, moving from purrs to barks. We apply that to our cat starting point, and you again can see the point where you end up, you were to follow that arrow, starting from cat, brings you closer to dog than to cat, your original starting point. So hopefully, if you're more visual, spatial inclined, this helps a little bit, but like Anthony was saying, the overall point is that we're trying to represent these words in a way that's meaningful, both for humans and for computers.
So does the computer now know how to, in computerese, create the sentence that you had up before? The dog barks, the cat purrs. Does the computer know that now?
That's a great question. So something I didn't cover here is we have representation for individual words. How do you put those together into a sentence?
Right.
If you were just to do something naive like add them together or average them or something like that, you wouldn't be able to tell the difference, for instance, between dog bites man and man bites dog. Right? You're just going to add them together naively. You can represent sentences. It's a lot more involved than this. This is already quite quite involved.
Okay.
So take my word for a similar approach to this can be used to represent whole sentences. And actually, we've gotten much better at that in the last 4 or 5 years. Before then, we couldn't really do it in the same way. So I know it's not really directly answering the question, but.
Do you mean that grammar can be broken down in a similar fashion?
The computer, we can, yes, use the same statistical patterns that we see in the text to have the computer basically learn its own representation of English grammar. Yes.
What would you ask the computer to get the sentence? You know, the cat purrs, the dog barks. I mean, how does this help us relate what you ask AI to do and what it spits out?
So unfortunately, that's going to be a little dependent on the application. So if you're asking it to produce that sentence, it might be, depending on what techniques you've used, it might be as simple as you type in, I forget what you gave, but the cat bit the dog or something like this. You just feed that in, and it would give you a sequence of numbers that's its representation of the cat bit the dog.
And what would you do with that?
Ah, great question. So that'll feed into the very next part of the talk. So excellent setup. I planted her in the audience. Just a couple slides before that, I just want to note that just for your erudition, the same technique that we just used is equivalent to perfectly training a neural network where you're asking it to given a word, predict the probability of another word occurring in the same sentence. So the weights of this neural network would be the same as this table in some capacity. And in actuality, because the English language is something like 400,000 words, something along those lines, and growing daily, having a 400,000 by 400,000 table is not very practical. So you have fun, more sophisticated ways of getting a neural network to learn those representations rather than doing the calculations by hand like I just did. So that was just meant to be illustrative. So now we covered, all right, we know how the images are represented. We know how we're going to take text and represent it for the computer. Now, one of the things you might do with the text is try and generate an image from it. So, going back to this previous slide, we're going to take this text and give it to one but not both of our denoisers. So it's important to know what's a denoiser. This is the essential task the denoiser is trying to accomplish. So this is a tiger. I don't know how well you can see it, but we'll zoom in on it a little bit later, so don't worry too much. But this is a tiger with some sort of static laid on top of it. You can almost think of it like a film grain or something like this, right? And the goal is when we apply this denoiser, what we're trying to accomplish is take an image that's noisy and figure out what the quote-unquote original image was. So try and get rid of all of that noise and produce a pristine version. So if we zoom in, and hopefully folks will be able to see this. So if we zoom in on just one part of this, I'm showing you some of the noise here, right? And you can probably just barely make out there are these little almost confetti-like dots on top of this. As a human, if I were to tell you, all right, take this image and give me the original out, get rid of all the noise, you'd actually probably have a pretty good chance of doing that because you can look at different regions of the image, like this black stripe, and go, all right, well, I know it's not supposed to be like a bright pink pixel in there, so I'll make that black, so on and so forth. You can do that for this entire image. It would be arduous and time-consuming, but you'd probably do a pretty good job of, not a perfect job, but a pretty good job of reconstructing what the original image looked like without all that noise on top of it. So this is what you might do, or what you might if you're going to use like Photoshop or some off-the-shelf tool like that. This is what it means by denoising, trying to identify and remove noise from the image, like I said, like film grain. What we're asking in this case our computer to do is to complete random noise and produce a tiger. How can that possibly work? Well, it all depends on how we train the neural network to do this. So, as an example, we'll start off with, just as we did before, a bunch of handwritten images for this example. For each of those images, we are going to generate varying levels of noise. So we're going to generate, here's what 10% noise might be, here's what 100% noise might look like, right? And then apply that on top of the image. So now, from this one image, we have 10 different images, and you may have more or less in practice. And we know exactly what we add for noise to get to the noisy, staticky image. Then what we're going to do is take a neural network feed in the noisy image, feed in how much noise we added to it, and ask the computer to produce what it thinks the noise was we added to it. And we know that because we generated the noise in the first place. So we use the same sort of training operation, this sort of guess and check approach for this. And you can do a pretty good job if you feed it a bunch of different examples and game the computer to take a noisy image and remove the noise from it. When we use this for image generation, what we do first is we take our initial starting image, we ask the computer to predict the noise, we remove the noise that it predicted from that image, and this will be okay. It normally does an okay job of this. Then very cruelly, we add back in more noise. We add more static into the image, but slightly less than we started out with. So you might start out with an image with 30% noise, you add back in just 20% noise. And you have the same feature happen again. And you do this over and over and over again. You start at really high levels of noise. Like I said, at the beginning, you start with an image that's complete static, completely random, and ask it, try and denoise this. And if you start it with something that's completely static, if you're a human, if you're a computer, it doesn't matter. What you're going to produce is not going to look very good. But it will maybe have some things in it. Then you add noise back in and say, all right, well, now it's a little less noisy. Try and denoise this again for me. And you keep doing that less and less and less. And as you go through this process, an image emerges. And the one important thing to note, the way that we get the computer to produce the image that we want as opposed to any random image it wants, is we do this twice. We do it once with just the image and the amount of noise, and we do this again with the image, the amount of noise, and the representation of the text we want to produce, right? And because of this, there are going to be two slightly different results. Like I said much earlier in the talk, we compare those results, and the ones that, the differences between these two, the ones that came from the version of this denoiser, which were given the text we want to produce, what this image is supposed to end up being, we sort of move more in that direction. So what this actually ends up looking like, and the sort of intermediary images it produces when it's going from complete static to an actual image are this. Oh. So this is the initial completely random noise we start off with. And we say, this is supposed to be a cat in a party hat. Denoise this, knowing it's supposed to be a cat in a party hat. Well, if you start off with completely static, it doesn't do a very good job. You know, it's not a lot of information to go on. But there's some little components that appear. Like you can see, this is starting to get a little bit more purple, a little bit more purple. As you go on, there's some of these almost triangles that are coming out. Just these very, very faint features. As you keep denoising this over and over and over again, it has more from its sort of previous iterations to latch onto and go, oh wait, that could be a nose, that could be an eye, that could be an ear. And as you keep going on, it eventually produces the image you want of a cat wearing a party hat. So that's what this actually looks like in practice.
How long does that take?
That's an excellent question. It depends on a few things. So it depends on, like I said, in my example, I gave 10 different levels of noise that you might add. In reality, that might be thousands or tens of thousands of very, very gradual, minute steps you're taking. It also depends on how powerful the hardware is you're running this on. So it can vary. And I guess I should re-emphasize what I'm describing here is a general technique that's used by many different actual implementations. This quote-unquote diffusion technique has a lot of different variations that are being used now. So it also will depend on exactly what else you're doing to generate these. So sorry, I know it's not that satisfying, but to give you just anything concrete, when you go to, let's say, one of these free online tools and ask it to generate an image, depending on what quality you want, it'll take something on the order of seconds, like 10 seconds.
Could you ask the computer to show me a cat with a purple hat?
So for this particular slide, I didn't, but a man named Stephen Wolfram did, and so this is his result. But yes,
But
someone
that's
asked
where
him.
it started. Someone said, show me a picture.
Exactly. Give me a picture of a cat wearing a party hat, and this is what it produced.
How
Yes.
does the computer know that the image is finished?
It doesn't know. We are the ones who are saying how many iterations we want to go through, so we decide at some point that it's done. Yes.
I'm assuming all these images are either on a screen or can be printed onto paper.
Yes. Yep.
Could AI ever make anything with oil paint on canvas?
Absolutely. Yes.
Oh, no.
So the question was to do with whether AI could, whether this is only digital images or anything else. A printer is almost like an ink painting, right? It has ink in it and it's sort of placing dots. I don't know that anyone has done this with generative art like this before, or generative images, I should say, like this before, but I've seen other setups where someone just literally has a robot, it has sort of arm, and it's holding a paintbrush and painting on a canvas.
Oh.
So yes. Yes.
I'm really never gonna ever generate my creativity or my ideas. And I was a teacher for 30 years, and I always told my students that that the one thing they can compete with computers is with new ideas and being creative. Now I see that because there's so more powerful computers, and they can take all our ideas and they can do it faster. We're gonna compete with them, so I kind of want to know, I'm an outcome person, I want to know outcomes. That's from all this.
So I'll talk a little bit about my perspective later on to talk about what potential outcomes might be from this technology. But I will say a couple of notes here. So one important thing is to train these models to do this denoising, we feed in a bunch of images from the, are produced elsewhere. So photographs people have taken, art people have made, so on and so forth. I don't have, unfortunately, anything to illustrate this, but it turns out that if you don't use things that are produced by humans to train these models, so if you just take one initial model you've trained maybe on human data, on human photographs and paintings and so on and so forth, and then have it produce a lot of art and train another model on that art, and then do the same thing over and over and over again. So not having any sort of human input in there. Over time, the quality of the images it produces drops off significantly. So these, at least right now, using this state of art technique I'm describing, it is piggybacking on things humans have done and produced. So that's one thing that might assuage some of your fears.
That'll make art, you can always make art that's human.
I will leave that to you. That's a controversial statement, I'll say. The other thing I'll say is, in this case, right, who decided that we want a cat wearing a party hat? Some human said that's what I want to produce. So the AI isn't coming up with ideas on its own necessarily. To what extent you consider that to be intrinsic to creativity, I'll also leave to you, but maybe that helps lower your anxiety a little bit, at least for this portion of the talk.
So it won't saturate the market and say,
We'll get to that later.
Can I just go back and say,
Yes.
there was apparently some big thing going on, that someone had taken a picture of President Biden and put it on something. I sort of missed the drift of it, but they just took a picture of Biden out of the newspaper, out of something, and then created it, instead of the cat in the hat, had Biden's picture in the cat in the hat. So they worked with something they had, said make a picture of President Biden with the hat. That's fairly frightening.
Yes. Yeah, I mean, if you think about the examples, so I guess the question, I keep forgetting to repeat questions. The question was around, essentially, can this be used to produce propaganda or faked photographs or things like this? The answer is yes, it's very good at it. They're photorealistic. It's very hard to distinguish from real photographs. I think the effect of this on the upcoming election will be interesting. And not only that, I've actually, sorry, not to ramble, but I've actually seen what you're talking about with videos as well, not just images.
Right.
So,
Right.
food for thought. So now I've gone through this entire process, top to bottom. I've told you how we are going to represent the images. I've told you how we're going to encode the text we want to generate for the computer. I've told you how we're going to denoise this initial static image and gradually produce, some quote-unquote AI art. But I imagine that many of you will be unsatisfied. I've told you exactly how everything works, but it's still pretty mysterious what's going on. How's it going back to this cat example? How did it get from here to there? The answer is no one knows. No human on the planet knows how these work. And I'm being dead serious. So because of the way that we're having these computers learn, because we're just using the sort of hunt and peck method that doesn't have any human in the loop and involves randomization to some extent and so on and so forth, and because we're using this very generic neural network architecture that can represent a lot of things. I mean, like I said earlier, it can represent any computation that you can do at all in the human brain or in a computer or whatnot, you can represent with a neural network. But because we're using this randomization approach, it is very difficult to tell what you actually end up with and what it actually has implemented. And I guess to put a finer point on this, so as humans, both of these things make sense to us, right? The sentence, Christian Bale fighting a kangaroo, has some sort of meaning to us. We understand what that means. And if we look at this image, we see, oh, that's, you might not know it's Christian Bale, but that's some man and a kangaroo, and it looks like they're fighting, right? To the computer, what we've actually given it to work with is this. So this is the encoding of Christian Bale fighting a kangaroo, and this is the encoding of, actually not this entire picture, but just, I don't know if you can see this very corner of the picture right there. So we're giving it a whole bunch of numbers and saying, I want to get out of this bunch of numbers a whole separate bunch of numbers, a huge number of numbers. If you were to, my opinion, if you were to sit someone down and gave them thousands or hundreds of thousands of examples of here's one number, here's a number it should turn up as, right? And try to have them figure out the process for doing that, they would never get anywhere. Maybe they could find some little correlations or something like that, but people would not be able to figure this out. This is why we have these machine learning techniques where we just have the computer figure it out on its own, but the consequence of that is that we don't know what the computer figured out, or we don't know how the computer manages to do what it did, except in some very, very trivial examples. So to help highlight this is not using a neural network, but this is using a different optimization technique called genetic algorithms. I believe this is from 20 or 30 years ago, but basically NASA had this problem where they're going to launch, I believe, a satellite. They needed to have a particular antenna that had some really, really stringent requirements, so it's space requirements, and had to, pick up a certain frequency and so on and so forth. And basically, they use something very similar to the random approach that we were just discussing for neural networks to say, hey, make me an antenna, the best antenna you can. So the computer tried one thing, and then tried another thing and said, well, is the second thing better or not? If yes, keep it. If no, ditch it. Keep going, so on and so forth, right? These are the antennas it produced. To refresh your memory, this is what a normal antenna looks like, right? So these are things that no human engineer, likely no human engineer would have ever come up with. They worked better than any of the human engineered designs for this application. And I believe it's not true anymore because people put some research into this, but at the time the computer produced this, the engineers at NASA didn't understand why it worked or why it was more effective than traditional approaches. A second example. So someone asked a neural network, in this case, to try to learn how to add two numbers together. So it was just given the text of the number, the digits of the numbers. Someone trained it. It's not so hard for a neural network to catch on and learn how to, given two numbers, put the sum together. But then the same person who did that experiment spent months looking at the individual weights and thresholds of all the perceptrons and try and figure out, okay, this thing has learned to add two numbers together. What actually happens when I give it those two numbers? This is the answer. This is what it learned for how to add two numbers together. I think suffice to say, this is not how humans normally learn to add numbers together. This is much more complex. It's a little bit hard to describe. This is almost like treating the numbers, the individual digits of the numbers, like they're sound waves or waves on a pond, sort of. This is very poetic language I'm using, but to give maybe a little bit more insight into what's happening here, it's almost treating the numbers like they're on a clock, and it figures out, for instance, if 10 were midnight on the clock, it's almost figuring out when to carry digits over by saying, all right, did we go past midnight, and how, if so, how much, right? To give you like a very, very vague statement about what it ended up doing. But again, not normally how humans think about numbers. And so someone else was very interested in this. They reran the experiment, and their neural network learned something completely different, a completely different way of doing addition. That again is not how humans do it and non-intuitive. So we are at a point with this technology where our grasp exceeds our reach in terms of understanding. We can do things and get the computer to do things, we don't understand how it's doing them. All we know is, or we can be fairly certain of, is whatever sort of, if you will, thoughts it's having or whatever concepts it's representing aren't like what's happening in human brains. And to bring this back to generative art, that's why you get strange examples like this, right? Like some models, for instance, have difficulty distinguishing, all right, a person's beard from another person's hair. So if you think about the sort of denoising process that we went through, you can imagine maybe why this is happening. There aren't necessarily coordinations between different parts of the image, so maybe it started off generating this person's, it saw something that looked a little bit like eyes, and it saw something that looked a little bit like eyes there, and went, all right, I'm gonna put two people, and then the hair kind of ends up meshing. But obviously, well, unless they were trying to make some sort of statement or do something novel, you asked a person to make an image of another person, they would never make this. This is reflective of some sort of fundamental misunderstanding going on inside the neural network that we don't have access to, exactly why it thinks this is what a person might look like. And likewise, actually this has been mostly fixed, but in older models, and by older I mean 3 or 4 months ago, because that's the rate of progress here, it had real trouble with hands. It couldn't figure out how many fingers people should have or anything like that. And you really start to look at this one, there's some other, the teeth are, something's really not going right here. Again, all we know is that something strange is going on inside the head of this neural network, and we don't know why it is that it produces images like this. Last, just another silly example. So it can also misinterpret what you mean. So this is if you give it, if you ask for a wiener dog race, it doesn't understand that you're not sitting on top of the wiener dog racing the horses. You're just letting them race themselves. There are no jockeys involved. So this is maybe you could imagine a small child making this sort of mistake or something like that. This is a little bit more intelligible, but again, just to say that whatever's going on, the brains of these neural networks is very dissimilar to what humans do or how humans normally think. And so, Anthony, to get back to what you had said earlier in the talk, it's very important to keep in mind how we think and how the computer thinks is not the same thing, and to try not to conflate them, because some really strange things are probably going on inside its head. All right, so now this is probably the most anticipated portion of the talk, which is where's this all going? And you'll be glad to know that I'm mostly going to be talking about economics, so it's going to be scintillating. But seriously, I think that economics can provide some useful insight. Looking at the past basically can provide some useful insight into what the future might look like. So the very first thing I'd like to talk about is an effect called Baumol's cost disease. So if you have the autobiography of Agatha Christie, she has a part of her autobiography where she's sort of opining on her youth and how things changed between when she was born and when she was writing the autobiography. And one of the things she says is, I never imagined that I would be so poor as to not have servants, but so rich as to have my own automobile. So what befell poor Agatha? Well, it wasn't that she was destitute. She did grow up in a very wealthy family, but despite the odds, she became even wealthier than she started out. I think in the 1950s, she was making something like the equivalent of $2.5 million a year off of book sales. She sold more books than any other author in the English language, apart from William Shakespeare. I think third is Danielle Steele. She had a 300-acre, beautiful 300-acre estate in the UK. So the problem was not that she was no longer well off. In fact, it wasn't specific to her. So this is a map of the UK, or I'm sorry, Britain rather, from 1851 to 1901. And you don't have to look at this very thoroughly, but what this is showing you is a heat map of the proportion of households with live-in servants. So the red parts here are more than 30% of households have live-in servants. The blue parts are, mere 5 or 10% or less. So having live-in servants was commonplace in 1851. By 1901, it had become much less commonplace. Obviously, that trend would continue, where virtually no one has live-in servants today. And an interesting observation is that if you were to really study this map, you'd notice that in 1901, the places where there were still high proportions of households with live-in servants were the more rural places. The cities, generally speaking, the trend accelerated much faster where people no longer had live-in servants. So it wasn't, in fact, the more developed places, where industry was happening and there were lots of jobs, where people no longer were able to afford servants. It was the rural places. And the explanation for this generally is Baumol's cost disease. The people in the cities, if you think about being hired on as a servant in, 1800, or maybe earlier, let's say earlier, 1200 AD. Your options might be, I can be a subsistence farmer, I can starve, or I can be a servant. So if you imagine how much you have to pay someone to be a servant, it's only a little bit more than whatever they'd be making by doing subsistence farming, which is not a great deal. In the as the Industrial Revolution ramped up, especially in the cities, there were a lot more opportunities for people. People had a wide range of new jobs that they could embark on, like building automobiles, that didn't exist before and could provide more value to society than just waiting hand and foot on a particular family day and night. And because of that, to entice them to keep working for your family and living in your house, you had to compete not only with subsistence farming, but auto manufacturing, textile manufacturing, so on and so forth, right? So similarly, in the past, Architecture, I think it's generally recognized, used to be a lot more ornate and a lot more detailed and complex. So the 3 examples I have here, this is the interior of Hewitt Hall in Edinburgh. This is the Karlskirche in Vienna. The last one is Grand Central Station. And I don't think I have to show examples to convince folks here that today when we build big skyscrapers, generally they don't have huge amounts of gilding or these intricate sculptures embedded in them or any of these sort of nicely features. Why is this? Well, between when someone was building a cathedral during the medieval period and now, that same person who might have been building the cathedral has a lot of other things they could be doing, and so you have to pay them a lot more, right? That same person could be doing more complex and meaningful, what we might consider as society more valuable things like building the Large Hadron Collider or working on a microprocessor. These are sometimes called miniature cathedrals because of the sheer complexity. Or even it turns out, the growing trend is you and a couple of your buddies can start a company and make millions and millions of dollars, especially if it's an internet company or a software startup or something like this. So, how many people are, compared to the cost of the building outright, to add all these fine decorations, you have to entice people with increasing amounts of money because there's so many other opportunities they have in society. So, in the future, if we have AI systems that can generate and design architectural features on their own without any human input, and perhaps even generate or create the actual physical items through 3D printing or something like that, I would expect that a trend would be, we can, again, this is very hard to predict, but we might be able to see more ornate architecture, more elaborate custom design work than we were in the past, because it'll be much more available. Another economic phenomenon, Jevons paradox. So, why is the cost of gas always so high? Well, gas is a commodity, and so it's subject to simple rules of supply and demand. So, the supply, it turns out, of gasoline has only gone up. So right now, in 2023, we produce more gasoline per year than any other year in the past. At the same time, fuel efficiency in cars has gone up. So with the same amount of gas, you can go further in your car. So it seems like the supply has gone up and we have more efficient cars. Why is the price of gas still always relatively high compared to the past? Well, turns out if you combine more oil and more efficient automobiles, people drive more, right? They can afford to drive more because they have more efficient automobiles and there's more supply of gas. So even though if we drove the same amount, the price of gas would go down, there'd be more supply and the same amount of demand, we actually ramp up our demand and even actually, in some cases, go further than the original demand, and so the price stays high. This was Jevons noted this again during the British Industrial Revolution, where they had figured out more efficient steam engines. So they thought, all right, well, last year to power the nation's workhouses, we used this amount of coal. We have this much more efficient steam engine now. We should be able to reduce that by a considerable amount. What actually happened is not only did the consumption of coal remain the same, but it ramped up because there were so many more applications of more efficient steam engines to different industries, different parts of society. So with AI-generated art, you might imagine that we will ramp up our desires for unique artworks or things like that because of the higher availability of them. And in fact, even though now it might take 10 seconds to generate a beautiful painting, that might not be enough. We actually might want to be generating even more images than that for reasons that are hard to fathom maybe, but for instance, I don't think anyone today has wallpaper where every single blotch of the wallpaper is a completely unique portrait of themselves or something like this, right? In the future, if it's much easier to generate those images of yourself, you don't have to hire someone to do that, there is likely to be more demand for that. And so sort of harping more on this uniqueness, this could create some really strange effects in society. So here's a little fun game for you when you get home. You can sit in one of your rooms and just look around and take a tally of the objects in your room, how many are unique, handmade, one of a kind, no one else has that same thing, versus how many are mass produced. For most people, it might be a little different because I know that we're art aficionados here, but generally speaking, the mass-produced stuff that you could go to Walmart and buy again if you needed to is going to outweigh all the unique items you have. In the year 1000, this wasn't the case, right? Everything you had was unique. All your glass was hand-blown instead of being manufactured on an assembly line. Your mattress was one of your most important and expensive possessions because it took a lot of goose feathers to stuff the mattress. You handed down, wills oftentimes were basically only talking about mattresses. Now you can see there's a factory here, there's 2 guys running something like 10 machines that probably is churning out hundreds of mattresses per day in this one little factory, right? So in the future, if there's one of the constraints for the uniqueness of objects that you own is someone has to design those objects. You have to manufacture them later on, yes, but it doesn't really, if one water bottle works pretty much just as well for everyone, there's not a lot of justification in spending a lot of time designing different variations of that water bottle, maybe colors and like that, but if it were as simple as asking the computer, hey, make me a cool, interesting new water bottle, you could imagine a future where you step into someone's home and everything they have is unique. Everything is tailor-made to their liking, and nothing in there is anything you've seen before. And you can't buy any of it because it's all one of a kind just for them. Or maybe you could ask them for the code to regenerate it. But. Likewise, you can imagine if it's very easy to make a lot of different designs, it'll be very easy to tailor things to your specific tastes and interests. So I don't know if anyone else has ever had this experience, but maybe you go over to a friend's house, they say, oh, this is a great movie on Netflix, let's watch it together. And they open up their Netflix recommendations, and they're completely different than yours, right? And you go, oh, I didn't even know that that show existed or was on Netflix or what have you, right? This also, one of the sort of key aspects around why the internet and YouTube and things like that have started to take big bites out of cable television is Netflix has this wide inventory of shows. Based on what you watch and based on what you like, it can start to tailor its recommendations for those shows to you. YouTube, very similar idea, but it doesn't have shows. It has millions and millions and millions of user uploaded videos that it can recommend to you. And so somewhere in those millions of videos, there's probably going to be something that interests you or appeals to your tastes, and YouTube will try to learn that. There was a recent episode of the new season of Black Mirror where they envisioned, hey, maybe in the future Netflix will generate, using AI, a show just for you, specific to you, not for anyone else's consumption. So you could imagine a world where not too long from now, we might have artificial intelligence models that can produce infinite amounts of content, video games, art, text, writing, whatever, that is not only specifically tailored to you, but so compelling you might not be able to look away. And in fact, going back to the example about home decor, I don't know if folks saw recently Apple announced augmented reality headset. You might imagine, well, what's the point in having actual physical items? You could sit in your house and have the AI decorate your house as you like and walk around sort of in this fantasy world. In fact, maybe you don't even have to generate things that are realistic. it could generate a complete fantasy world for you to live in. And maybe not only in your house, but this is downtown Boston, maybe your entire world is going to look like, an impressionist painting or a cubist painting. It'll be difficult to navigate or something along those lines, but suited to your taste. So people might not actually be seeing the same things as each other. And here, just to really put a fine point on it, here's an example of that. So this is a video where someone speaks into their AR headset. They say, a plant with pink flowers or something like that. In real time, it generates, for YouTube is buffering, so this might not go well, but let me just describe what happens. It generates this photo that is placed in a location in the real world virtually, and the person can walk around and see this thing from different angles, right? So they have added this fake persistent model that the AI created for them into the real world. This is sort of a tech demo of that, but I think you can imagine that, especially given the recent pace of advancement, we can have much better examples in the future. This video goes on to show someone generating a painting, a Vermeer painting, and putting it on this wall. And the person can walk around, and every time they go past that wall, they'll see that. To make you feel maybe a little less creepy about this, I've also seen examples of people walking around with AR headsets in Manhattan, Times Square, places like that, where they're dynamically blocking out all the billboards and advertisements. So the person doesn't have to see advertisements. So, drawbacks as well as advantages. Last thing I wanted to comment on is the accessibility of art, from an artist's perspective. I'm not an artist, so, and my art history is a little murky, so please forgive me here. But back in the Renaissance period earlier, a big part of being a painter was producing paint, right? The techniques to produce paint, you normally use egg-based paint, procuring the materials for the paint, and so on and so forth. And so any painter would know how to make their own paint because it was a necessity. In, I think, the late 1800s, we started coming out with manufactured paints, so you could just go into a shop, buy the colors you wanted, you didn't have to think about producing them, and use those, right? And actually, now, today, you don't have to use paint at all. You can use a digital tablet or something like this and make digital artwork, and you don't necessarily have to know anything about how to work with paint. You don't have to know anything about brushstroke techniques necessarily, so on and so forth, right? So there are two perspectives you can take on this. One perspective is, well, it's great that you don't have to do all this sort of useless tangential stuff to be able to create great art. The other perspective you can take on this is, isn't it a shame that doesn't take any talent anymore? People can just go to the store and buy paint, not like the old days where you had to know how to do it. The barrier to entry or the amount of know-how you have to have has really been reduced, and isn't that too bad? Likewise, we're going to see the same thing with AI art, right? When you can just say, here's a sentence of what I want to generate. I want to generate, a man jumping over a rhino. It'll just spit that out for you. Or even if you're a commercial illustrator, you might be able to, someone might ask you, hey, I want something in this sort of style for a brochure I'm making or for, a billboard I'm going to put up. You might be able to produce one sample image and then they go, okay, that's enough, and generate a bunch of other images using that same style, training it using this same initial style. You might also imagine, hey, I'm an artist. I really have trouble with hands. I have this little model of a hand, wooden model of a hand on my desk. I try and use that for reference. AI art will allow you to do that, but to a whole other level. So another video, let's see if it buffers. You can see here, hey, I have an image of a dog, and I just want to manipulate this and get the exact sort of reference picture I need for a dog for the particular piece of art that I'm trying to make. So you can alter, head shouldn't be at that angle, it should be at this angle, right? And in real time, do these manipulations to give you a broader Potentially, or you could also imagine someone just using this and saying, all right, I've manipulated this, I've gotten what I want, and then I'm done. Since we're having a little bit of a bandwidth issue, I won't play this too much longer, but suffice it to say, when it becomes much easier to generate art, it's also going to become much easier to generate anything that you want. So, but I want to end on just one little anecdote. So all these prognostications I've just given you, I think there was a famous quote. It was Kissinger, who was visiting a prominent Chinese politician, I believe sometime in the 1960s, when this particular politician died in 1970, so could have been too much later. The Chinese politician was asked, what do you think the effects of the French Revolution in the late 1700s were on the world? The Chinese politician thought for a little bit and he went, too soon to tell. So it's very hard, especially given the rapid advance in this technology, to understand what's going to happen even a couple of months down the line, let alone a couple of years down the line. Right? Next week, Congress might issue a law saying, hey, anyone who touches a computer, we're going to summarily execute. So there are a lot of different possibilities, but these are the broad sort of effects that I expect might occur in the future. So thank you very much. I know there was a lot. Thank you for sticking with me. Any questions that I might be able to address? Yes.
I don't know who's in the right, I don't know who's in the right ballpark, but I saw in the calculus formula that if they use the word token, does that have any relationship with the NFTs, the non-fungible tokens?
So the question.
How does that relate to?
Yes. Yeah. So let me see if I can get back. Let me see if I can get back to the slide. But the question was about the word token was on one of the slides about, I believe, the interpretation of what was going on inside a neural network. Is that right? I'll sort of try to endeavor to find it, but what token means in that instance is either a word or a part of a word. It's sort of a term of art from natural language processing and linguistics. Was it this slide, perhaps?
A couple of slides had token in the calculus formula.
Yes, maybe this one. Anyway, in this particular example, what token means is, for this neural network that's been trained to add two numbers together, probably either a digit or a couple of digits together. How it relates to an NFT, it's not really the same thing. Tokens being used in a different way in NFT. So NFT stands for folks that don't know, for non-fungible token. That's really more of akin to a concept of transferal of property rights of art. So it's not intrinsically related to neural networks and AI-generated art. You could create an NFT of art that you generated with a computer, but it's not necessarily related. Anthony?
I have a question. I think there's so many people that don't fully grasp what artificial intelligence is.
Yes.
Can you maybe talk a little bit about the mythology surrounding artificial intelligence, and from your unique perspective, what do you chuckle at when people say that you're like, man, that's not even true?
Sure.
What is reality?
So I think the question was something along the lines of, what does artificial intelligence really mean? What are some common misconceptions? What constitutes artificial intelligence? So this is an interesting one. The goalposts for artificial intelligence always move, right? So in 1970, 1980, there's a widespread belief of, well, a computer is never going to be able to beat a human at chess because that requires logic and reasoning and creativity and strategery and psychology and all these different things. And then obviously Deep Blue beat Kasparov, and people said, all right, well, but that's not. It turns out we were just confused about chess. Chess is easy. Nothing special about it, nothing that is human specific to it. So that's fine. But people said, okay, but Go, the game of Go, that'll be, that really requires human level intelligence and insight to tackle. A few years ago, I think it was 2015, Google released AlphaGo, and that beat the pants off of the world leading Go champions. Likewise, people have said, all right, well, the bar for artificial intelligence is going to be, a computer can never write a sonnet or produce a beautiful work of art. Clearly, we've gotten way past that point. And in fact, Alan Turing, who was sort of the father of modern day computing, his criterion for what would constitute a general artificial intelligence would be if you sit someone down and have them have a conversation with two people, one of which is a computer having a conversation with them, and one of which is an actual person behind a curtain, so you can't tell who's who. If they can't distinguish between the person and the computer, or they get it wrong, then we've reached artificial general intelligence. In the last 2 years, we've not only gotten there, but we've shot way past it. So it appears like we now have systems, I'm thinking specifically of GPT-4, which exhibit a lot of characteristics where they might be called general intelligences. They not only can write you a sonnet or write you an email, they can also look at a picture and tell you what's going on in the picture. They also can create a business plan for you. They also can go out on their own and convince humans, real humans, and this is an actual example, to do things for them. So in this case, I believe OpenAI let GPT-4, this AI model, sort of out into the wild for a little bit, and let it sort of do its own thing. One of the things it did was, I don't know if you folks have ever seen CAPTCHAs online where, instead of get to a website and says, hey, before we let you in, to prove you're not a robot, here's this, these distorted words, write down what the words are, the letters are. This model still had trouble with that, although very soon that'll be solved. But GPT-4, this AI, had difficulty with that. So what instead did was it went online, it found a person through a service called Amazon Mechanical Turk and said, hey, can you write down, can you transcribe what this says? And the person went, and again, this is totally the AI model just doing this of its own volition. The person went, sorry, I missed one step of this, which is that in this mode they were running it, they could also see, they had a mechanism, I won't go too deep into it, to see its internal thoughts. So why it was going to do the next thing it was going to do, not just what it did. So its own reasoning or its own explanation. So the person asked, why is it that you want me to transcribe this? And what the AI thought was, oh, well, if I tell it I'm a computer, the person won't do it for me. And so what it said was, oh, I'm visually impaired. So, yeah, I don't know how much that helps, but helps answer your question, I guess I should say, Anthony. But basically, the artificial intelligence in general is being able to come up with solutions to problems. Is a very general way of describing it. There's a huge continuum of how good a person might be at doing those things. AI is just something that's not a human solving problems. And the degree to which it is able to, the degree to which it's successful in that is sort of the barometer for how artificially intelligent it is. I could regale you with some interesting stories about things that people thought AI could do that obviously it can't do, and it's just fantasy and whatever. Unfortunately, in the last year or two, a lot of those things AIs can do now. So it's hard to answer that question. It's just evolved so much in the last couple of years that it's, a lot of progress. Yes?
One last question. With the unpredictability of AI, and what do you think about regulations?
So the question was, because of the unpredictability of AI, what do I think about regulations? So a couple of things here. So one is, it's specific to the unpredictability. The real point where we're going to be in trouble is when and we're probably going to get there fairly soon, is when the AIs themselves can generate new AI systems and basically improve themselves. And past that, you get this sort of reinforcing cycle, and you'll get smarter and smarter and smarter computers up to some computational limits. You know, this is very speculative, but once we reach that point, it is impossible to predict what will happen next. People are trying to, a lot of people in the industry, a lot of regulators, a lot of general concerned citizens are trying to avoid getting to that point. The two things I'll say there. So one is, I hope one of the things you've taken away from this talk is that actually, you know, it might require a lot of computational power, but under the hood, this is very simple math that anyone can learn and anyone motivated enough can implement. You know, you could actually, the neural networks that we're talking about, you could create in an Excel spreadsheet if you wanted to and run them from that, right? So there's nothing stopping a private citizen right now from building an AI model. In fact, that's what most quote-unquote AI research has been up to this point. Now we're getting into the regime where you need so much power that you probably want to have a few $1 billion around to buy GPUs and CPUs and computing power to run and train these. But things always get faster. You know, these type of state-of-the-art models, 5 years from now, any teenager in their basement is going to be able to create them, right? So the other thing I'll say is there is a concept of, well, maybe we can add in something to our training procedure or the machine learning procedure to make these models good people, right? To only have them do the things we want and not, you know, go and kill us or become Skynet or what have you, right? Or maybe regulate themselves, maybe. Unfortunately, two things about that. One is that it is easier to build an unsafe AI than it is to build a safe one. You have to add the safety in. So if you don't know what you're doing or you don't care to do that, it's easier to not do that. Just like it would be easier to make a car without seatbelts, right? Something like that. The second thing is perfectly aligning the AI's ethics and values with human values. I believe from research that I have seen is mathematically impossible. So we're not going to be able to do that. And you know, I was mentioning earlier, you know, regulations on this, because they're going to be so easy to circumvent. They might have noble intentions, but unless we're doing something really draconian, like I said, like saying, hey, no one's allowed to use a computer anymore or something like this, or maybe not a computer that has more than this amount of computing power, it is going to be very, very difficult to actually prevent these things from getting out into the wild. Just to help illustrate this, right? This is an actual, I guess I should also say, sorry, not to go on too long about this, but I should also say, for AI to be dangerous or to have really deleterious impacts on society, it doesn't have to be that smart. So this is some research from, I think, earlier this year, where the authors were had a neural network they trained to try and create beneficial drugs for human beings, right? And all they did was take that same model and sort of flip the signs, so make like a positive and negative, if you will. And it was able to produce a lot of novel, never before seen toxins, very, very deadly toxins for humans, right? So you just change its values a little bit, and hey, it can create very deadly, you know, the chemical formulas are for very deadly compounds. That's going to be something that this inevitably is going to fall into the hands of, well, not inevitably, but very, very easy for this to fall into the hands of a lot of people. Very, very easy to even have this happen by mistake. You can imagine making a little coding error and having the computer do something that was the opposite of what you intended for it to do. So I don't have a lot of faith in regulations for preventing some of the negative impacts of AI. That's not to say that it's a foregone conclusion that those sort of disaster scenarios are going to happen by any means, but I just don't think if we're going to avoid those, that regulations are going to be an effective way of doing that. It can help penalize people who have made unsafe AI systems, but it can't prevent them from being made in the first place. Yes?
The big question, it seems to me, is how can you tell what is human generated and what is not?
Excellent
What
question.
is truth, and also, to your point, aligning to ethics and right behavior. Everybody got a different idea about that.
Yes, yes, yes.
How do you tell truth and the difference between human and artificial generation?
Yes, so the question was regarding how will we be able to distinguish in the future between real photographs, let's say, and AI-generated photographs, or any other media. So thankfully, this is one where we do have some solutions. So I actually believe there is a camera out on the market now. I don't remember who manufactures it, but the key point is when it takes a photo, it has basically a secret key, a secret signature. I won't go into all the cryptography for this, but that it applies to the photo. So when you receive that photo, if you have the right equipment, you can look at it and say, oh, I can 100% mathematically verify this is an actual photo that was taken with this camera and not something that was generated with it. So it's going to be onerous to implement this, but there are solutions for being able to create verifiable images and video that we know an AI hasn't tampered with or generated.
Which would also have an algorithm for editing and, this has been manipulated for truth and honor. Or, because that's one of the things is, having just artists manipulate.
We have good examples for, not outside of art, we have good approaches for that, but they're not in very widespread usage because.
Also voice prints and all, everything.
Yes, I do. I completely agree with you. AIs can mimic human voices now with a very little amount of recorded audio. So it's very likely in the future you are going to get someone calling you. They're going to say, "Oh, hey, this is your son or close friend or whatever. I'm off the side of the highway. I need $500. It's going to sound exactly like them. It's going to have a convincing story. It's going to tell you. It's all going to be artificially generated." So I would definitely expect that to happen in the future. Yes. Can what be traceable? Yes. So the question is, if someone creates something nefarious, I think like maybe an AI system or something, can we trace back who did it? I mean, the FBI is very clever and has really good methods for trying to do this. In the general case, no, but criminals are normally pretty stupid, pretty unsophisticated. So it can be, I forget, there was some, I just barely saw this news article, but there was some sort of, at least a few days ago, I think there was also one a few months ago where someone had committed a murder and before they were Googling, how to hide a body, where to, So, it's not always going to take a rocket scientist to figure out where something came from. You could be very careful and avoid that detection, but it's hard. Any other questions, comments, concerns?
Artificial intelligence or AI, what we would call conscious.
So the question is artificial intelligence conscious? So I have a Master of Arts in Cognitive Science. I have a very skewed perspective on this. I'm sort of like a consciousness abolitionist almost, so I don't believe, let me put it in these terms. So in the 1800s, for instance, scientists were trying to during the Enlightenment period, people were trying to figure out what constitutes life. What is life? Why are some things alive and some things not? And they went on this sort of wild goose chase for this élan vital, this sort of life force that they think, oh, some things must have this and some things must not have it, and that's what separates living things from dead things, and inorganic things from organic things. And as we learn more about biology, we realize that there's no real such thing as life itself. So there's people very early on, when they're trying to figure this out, were puzzled by well, life is self-replicating, but some crystals can also be self-replicating. So is that alive or not? And what we figured out was there's no one life substance or anything like that. Instead, there are all these different characteristics: metabolism, homeostasis, reproduction, that all put together are characteristic of life on Earth. But some other things on Earth exhibit one of those characteristics or a couple of those characteristics, right? My perspective on consciousness is it's the same situation. We don't understand neuroscience well enough right now to pinpoint what consciousness is. My prediction is when we understand it better, we will go, oh, there's not one such thing as consciousness. There are all these different attributes that create a so-called conscious experience. There's sort of phenomenological consciousness. There's this sort of narrative that you have of yourself in your head, of your life. There are all these different, there's this sense of self, self versus the other, and all of these different disparate things, one or more of which might be exhibited by other things in the world, and some of which actually in some very humorous studies that I could recount, you can violate in humans. So you can, for instance, through some setups, make someone behave as though a rubber hand is their actual hand, and they'll flinch and if you try and hit with a hammer, things like that, right? So all that to say, I don't know. I don't really believe in consciousness as a thing. But it's also somewhat, there's a famous quote or a famous thought experiment. Do submarines swim? Yes, no, maybe, but that doesn't really necessarily matter. It's more to do with the behaviors that they exhibit, right? If an AI can act as though it is conscious, people are probably going to, it's our natural human instinct to treat that as conscious. And the fact of the matter might be, might require hundreds of years more consciousness research to understand. So I don't want to make too strong a comment on it, basically. I will say our current systems we have today are not conscious, as a big, bold blanket statement.
Your life has gotten much better for your show. Can you show us the first few slides?
Oh, yes. So let me go back here. So I'll try and show you, especially some of these fun example images. So this is the, give it a second to load. A couple seconds to load. So this is the Rococo-style interplanetary rocket.
Okay.
This is the drawing with heavy cross-hatching of an elephant wearing a top hat. What else have we got here? This is a person scope being attacked by a giant squid. These were the two initial examples I gave you.
Oh, yeah.
So you can see in this light, you can see this woman is
It's
not.
much better now.
Yeah, this person maybe looks a little bit like a ventriloquist
Although I
dummy.
think I've seen her.
Yeah. I've seen her in my nightmares. And this one looks like a real photo. I'll go through a couple more of these, but this is the Greek philosopher on a computer example I mentioned. Again, this is just over the last year, so this is very fast progress. I think this was the month-by-month breakdown of advancements in these types of models. This was, I think the next one is the Wes Anderson slide. So you can see here, this does not look like it's still from a movie. This one definitely does.
Wow.
What else have we got? Flowers. So this is comparing to 6 years ago, and you can see These are blurry. I mean, they kind of look like flowers, but no one will take them for real flowers, right? Yes.
Just a rhetorical question. If the computer does not have self-awareness, how did it know to say that it's blind and not a computer?
So the rhetorical question was, how does the computer know to say that it is blind if it doesn't have self-awareness? So that's a very interesting question. The way that those text models are trained is by feeding it in a bunch of words. You take a huge corpus of text and you say, all right, I'm going to give you the first word of the sentence, predict me the next word. Then you say, I'm going to give you the first two words of the sentence, predict the third, so on and so forth. And so it's just predicting one word at a time, or actually parts of words, but we don't need to get into that. The reason why it says things like I and me and so on and so forth is it has seen that that's how people write and how people talk. And so it's just predicting what's the most likely thing that someone would say if they were trying to dupe someone into doing a CAPTCHA for them. The most likely thing someone might say is, oh, well, if they were a computer, it might be, oh, I'm visually impaired, right? But it's almost like you were handed a script and said, here are these characters. One character is named I, one character is named this other, fool I'm trying to trick into doing this work for me. And what would the next thing the character I would say is one way to think about it. Yes?
I remember when we were chatting before, you were talking about the current iterations of AI, and you compared them more to a tool that followed commands.
We don't have, we're maybe at the very cusp of, we don't really have what we would call agential AI. So the systems that let me put it this way, we do have that, but not to the degree of sophistication and the level of advancement as we have these other systems built up, especially over the last year. So we don't really have AI systems that, outside of very controlled regimes like board games, for instance, that have an idea of, I have wants, I have desires, I have needs, I have to interpret this environment and figure out how my actions relate to the environment to achieve my goals. That's not something we really have right now. Instead, what we have are things like, things that are trying, how should I put this? Things where there is a fact of the matter of what the right answer is. Those are systems we're really good at making. So if there is a fact of the matter about what it would look like for a purple whale to be on the moon, right? We're really good at having systems produce that. Or where there's a fact of the matter of, here's the first 9 words in the sentence. There is a 10th word that was written. Guess what that word is? We're very good at creating those systems, and there's been a lot of advancement in that. There's not as much sort of self-autonomous agents that can go out into the world and do things on their own. Does that touch upon that?
So basically, current AI follows the instructions of sort of like a driver.
Yes, yes. Although, obviously, people are trying to advance on that.
Yeah.
All right.
Thank you.
Excellent. Well, thank you again for attending. I hope you aren't scared too much.